Okay, so hello everybody. Welcome to our P2P Systems lecture. And first of all, I have some announcements. The new exercises online, which will be presented next week on Thursday. Here we have this exercise. The topics are free pastry, so you have to check this implementation, free pastry, and answer some questions about this. And then we have the academia network, where we have also some shorter questions with, for example, populating the buckets. Okay.
Can you please turn off the light? The contrast is...
Okay. If you say which
it is. This one.
Okay, all right. So last lecture we had web peer-to-peer, a real-world scenario based in Chord, globase.com, a location-based heterogeneous peer-to-peer network, Omnicron, which is an hierarchical heterogeneous peer-to-peer overlay using De Bruijn networks. And in this lecture we want to learn about improvements of peer-to-peer overlays. So we don't have a look on more overlays, but improvements of existing ones. And in the second part, I want to talk about scale-free networks. So which possibilities exist to model large-scale networks. First of all, do you have some questions regarding the last lecture? Because I didn't ask, sorry. No questions? Okay. So let's start with the first topic, the caching. We have some considered facts that the popularity of queries, the distribution of the queries is not uniform, and the caching mechanisms, or in general, caching mechanisms work well with non-uniform distributions. And the intermediate peers, which are participating on the routing, receive information useful for other queries too. So the query distribution, for example, for sharing applications, file sharing applications, are non-uniform. They are zip distributed or log normal. So for this distribution types, we can use caching mechanisms. So the question is now, how can structured overlay networks take advantage of the query distribution characteristics? So here we have a caching mechanism for Chord. But this idea can be transferred to any other DHT overlay. So first of all, we have this original Chord routing with fingers. We reuse obtained information, so which are received at the source of the query. So how can we reuse the intermediate peers? Yes, so let's skip to the example. First of all, we have this peer Q1, which wants some data from the node D. And here's the routing process to S1, S2, and S3. So now the intermediate peers like S1 could act as a cacher. So this is shown here. We have the same request first of all is forwarded to S1, which now acts like a cacher and restarts this query to D and get the information back after 2 steps and can pass this information to Q1. So if another peer uses this finger also, so we can okay, we receive this query and we can answer this query immediately because we have obtained this information and we act as a cacher. Also the node which sends the request first is now a cacher because he has this object now. So this is a probabilistic approach. So it only works well if the cache node is asked from for this specific object. So it works, for example, for popular objects. Yes, and we can handle it if we receive multiple requests on this object. Okay, the scalability of this approach. So which parameter can we vary? First of all, it's important to have a small cache size because we only want to cache the most popular files and not every file. Also, we have some additional messages for this because of the query redirection. As we previously saw, we need some additional messages to set up this cacher, and the number of these messages should be very small. So we have here a trade-off, inserting more complexity for deal with load peaks. Also, the incremental deployment. This means that not every node in the peer-to-peer network must understand this feature of caching. This is important as we cannot simply stop the whole peer-to-peer network to deploy new software. So it's important that peers with different versions are compatible with older versions. And this incremental means that every new node knows this new feature. So after a time period, every peer in this network will know about this new feature. Yes, caching is not replication because yes, the replication process allows to update the data reliably, but the caching does not. And also, this is the main point, as we are caching on random nodes, the information could be outdated. And this is a bigger problem. So we can, for example, insert something like an maximum lifetime of a cache entry, but still we are not sure to get the updated information. Okay, here we have the summary of caching in DHTs. First of all, the advantages. We have reduced routing costs and the incremental deployment. We don't need additional overlay networks, and we don't out-of-band signal is not required. So we don't need to specify other messages than we use for our DHT overlay. And we have a minimum additional delay on building up a cacher, but it's a very easy process and design. The disadvantages are that we have consistency problems in case of updates and deletions. So the cacher may respond a request with an outdated object, as I said before. To handle this, we could insert, for example, a hash of this cached file and can compare this with the original data to be sure that we have the up-to-date data from this cacher. But this would probably violate the incremental deployment point, because every node has to know this feature, because the node which get the response has to check this. Okay, also additional storage space is required, but this is not a big deal, because storage space is cheap. Okay, the simulation results, this last point is outdated because we did not discuss any simulation. Okay, now another feature. We have the simple replication with motivation first, that we are storing objects only on one node. So if this node is lost, if this node leaves, we loses this information. So the idea is to replicate data on multiple IDs per object, and the file is published under each ID, and a file can be looked up under its next ID if the lookup for the previous IDs failed. And the number of replicas is flexible, but we will see another point about this. So for example, we can introduce multiple hash functions for the replicas. For example, we have we use the first hash function on this object to get the first ID, and another hash function on the same object to get another ID, where we can find replications. Another example is the sequential hashing. So we just concatenate the hashing. So first of all, we have only one hash function. We hash our object. This is the first ID. And if we again hash this ID, which is mentioned here, we will get the second ID. And so on. We can hash again the second ID to get the third ID, and so on. So we have something like a chain. If you remember, in web peer-to-peer we use the same for the username list to save the certificates. Yes, and also the responsible node for a particular ID should always check its replica whether they are still online, and has to refresh this replica. A small evaluation about this idea. Yes, it's easy to implement, as we have only this chain of replica, and we have a lot of shortcomings. For example, that the hashes of ID I and ID I plus 1 are not close. Yes, each one requires a new lookup. Yes, and if the number of replicas is fixed, for example, I equals 5, we have too much replication in a stable scenario and maybe too few in a dynamic scenario. So it's very difficult to find here a sweet spot with fixed number of replica. Also, if the number of replica is flexible, yes, which is, for example, determined by each holder, and he can adapt concerning the load or churn risk. Yes, and the main question of the flexible replica is how do I know that? How do I know when this chain is at this end? So, for example, the responsible node for ID. So the responsible nodes for the IDs, ID I to ID I plus 5 can go offline, for example, and the responsible node for ID I plus 5 plus 6, sorry, can be still online. So we don't know when this chain ends. Okay, but there exists an improvement of simple replication, which provides replication around a single ID, so not independently like this simple replication, and this is called PAST. PAST is an extension of pastry, what you might expect. Yes, it's an extension of pastry. The authors also developed script, split screen, etc. And the idea is to store objects on the car further nodes in the leaf set. Yes, instead of just storing them at independently IDs. And this PAST uses an API, a key-based routing. For example, we have this method here, replica set, which returns an ordered set of pairs on which replicas of an object with a given key K can be stored. Okay, and also we have a method update. It's an upcall, and it informs that a node has either joined or left this overlay. So we are always up to date on the replica set. The nice feature is that if the responsible node fails, a node from the replica set will be the new responsible node. Okay, here we have the evaluation of PAST. Yes, we only need one more lookup to find an object because the replica is in the leaf set, and the replication ratio is flexible, so this might depend on the object peer properties. And the responsible node is also responsible for the size of the replica set, and he can vary it depending on the churn rate or the leaf set of the leaf set and the own online time. And failed replica nodes are detected by the overlay, as we mentioned before, by this upcall update, and this is quite comfortable. We have also some drawbacks. For example, the replication is not peer heterogeneity aware, so weak nodes might be overloaded by the replication task. And also, and the security of this past, yes, the replicas are all in one ID area, so it's very easy to attack it. For example, in the simple replica, the replica are located at different independently IDs, so it's difficult to attack this. Okay, besides caching and replication, we can also improve the routing. First of all, a short motivation. So we can support multi-dimensional applications. For example, we had some multi-dimensional applications like location-based search or geographical mapping. And the idea is that we can create a d-dimensional ID space like we did in CAN and match geographical map to a two-dimensional space. This allows a location-based search, and yes, we can create search space for items with multiple attributes. For example, we can use the device type, memory, CPU, storage space. Yes, okay. But the replication could be difficult to implement on this d-dimensional ID space. Oh yes, we have the drawbacks, sorry. We have lookup complexity, which increases because of this multiple dimensions, which is now d multiplied by log n to the power of d to a power of -1, and we have no replication. Yes, and it's difficult to implement it. Now, in contrast, we have the multiple realities, a small motivation. We want to use an overlay multiple times. So, for example, we could use 2 chord overlays here and here, and in this chord overlays we have we are located at different positions. For example, we could be this peer with the ID 709 in the left overlay, and on the right overlay we are the node with the ID 2906. And yes, we use several overlays in parallel, and yes, as I said, the peer IDs are different, but the object IDs are the same. So the data, so one object is only lost if different nodes in the overlays fails at the same time. And this is something like a replication. So we get a replication with this multiple realities. Yes, while routing, if we, for example, want to reach the node which is responsible for the ID 0, we could use this reality, for example, because we have here a very high ID, and we are near the 0 ID. So we can use this for the routing. So we can have them speed up here. Okay. So now we want to compare the dimensions versus the realities. Yes, both approaches reduce the routing path length, and they increases the node state and the maintenance overload, as a node has to save more contacts in different dimensions or realities. Yes, and one more dimension lead to shorter path lengths than by having more realities. For example, if you use a two-dimensional chord, so you have nodes on your x and y axis, then the paths are shorter than having two chord rings, even with the same number of neighbors. Okay, and more realities lead to an increased robustness through replications, as I said before. Okay, do you have questions to this topic? Okay. Another improvement is to overload zones. This pattern we saw in Omicron, where a zone must not be maintained by only one node, but a few nodes. We can also use this for CAN or GLOBase, for example. As you can see here, we have an example for a two-dimensional CAN. So every zone is maintained by a few peers. Okay, the motivation is to increase the robustness, and we can shorten routing paths because we have less zones with the equal number of nodes, because the nodes in one zone are connected to each other. Okay. And the idea is, like I said, we have now zones and areas which are managed by several nodes, and one zone is called here a virtual node, which contains a set of nodes. And the maximum number of nodes per zone is fixed. And if we surpass this maximum number of nodes, we have to split this zone, this virtual node. Okay, yes, and here are some conclusions. A node in a zone must know all other nodes in the zone. Okay, we have something like a mesh, maybe. And all indexed objects in the zone are maintained by the peers here. For example, in Omicron, we saw that there are some, you can delegate some tasks to nodes, because, for example, a node can maintain the objects because he has a better bandwidth. So we can use here the heterogeneity of the nodes inside one virtual node. Yes, and also a node from each a node of a zone has only to know one node of each neighboring zone. So we have the choice to, for example, we are in this zone, and we can choose to which node in this zone we want to have contact. So yes, we can use, for example, the locally close nodes to reduce the delay, for example. Okay. Okay, first of all, the advantages, the benefits of overloading zones. We have virtual nodes, which are easy to maintain. The node count is limited per virtual node. And we have flexible replication, as all nodes in one virtual node share the same objects. So we have a built-in replication mechanism in this overloading zones. Yes, and we can support geographic aware routing, like I said before, so we can choose the neighbors of the of other zones. So why is this not used more frequently? Here are some shortcomings. Yes, this works well with clear and static zone boundaries, but yes, it's not the praxis, because we have dynamic nodes and dynamic boundaries, and also we have here an increased complexity. Okay, the next topic is the underlay aware P2P topology. The motivation for this is that we want to know about the underlay to fasten our routing. So we want to, for example, pick nodes which are which have a good connection to us, or we have a short delay to these nodes. Okay. Yes. So for this the overlay requires information about the network topology and the state, and other underlay path properties like the locality, bandwidth, latency, jitter, loss, geolocation. And for example, we have to know about network address translation. So whether a node uses a NUT and is not reachable from outside, so we have another delay to route via an NUT traversal. Stun server, for example. Yes, and we get this underlay information from end host measurements. So we measure, for example, the connectivity to other nodes, but it's very costly. Yes, so every node has to know how good is the connection to another node. And yeah, we could also get underlay information with ISP feedback and through third-party measurements. So now we come to the issues with the underlay. So the underlay is everything below the overlay and abstracts the lower layer levels, like a physical layer, the MAC layer, the network, and transport layers. Yes, we have some parameters through which the underlay affects the overlay, the ISP-location, for example, the latency, the geolocation, and peer resources. This is just an overlay overview slide, so we go more in detail through this. Yes, and the underlay information is obtained through collecting, measuring, calculating, and estimating. Okay, here we have an overview of the underlay awareness. First of all, the ISP-location awareness. The definition is that the ISP location is defined as the ISP through which a peer connects to the internet. The benefit is that it helps in reducing inter-ISP costs caused by P2P traffic. This is also an overview slide, so we go in more detail on the next slide. Then we have latency awareness. The definition is that latency is the delay in information transfer between two nodes. Geolocation awareness, yes, this is the geolocation of a physical, is the physical location of a node. And we have peer resources awareness. So this is the definition. The definition is that a peer has resources like the bandwidth, CPU power, memory. And yes, okay, so now we go through all of these awarenesses. First of all, the ISP-location awareness. Okay, the local ISPs provide connectivity services in limited geographical areas, as you might know. The transit ISPs, so these transit ISPs, act on a global plane and supply the connectivity to local ISPs, or between them. And this is the main point, the traffic over transit ISPs is expensive. So yes, so this traffic is always expensive. So it's cheap for an ISP to hold data or hold the traffic inside his network or its network. Okay, for this reason we might have preferable contact to peers from the same ISP, for example, telecom. Okay, so we might choose neighbors from the same ISP. What are the benefits and shortcomings? We have a biased neighbor selection because we first of all have to check whether a client is from the same network. And we have a clustering of the network. So it's easier to understand, I think. And we keep as we keep the traffic inside the ISP, we reduce the ISP costs and have a lower delay. But yes, the save ISP costs point is not a profit for a peer. So it's only on the side of an ISP. So yes, a client peer does not matter whether he is connected to a peer in Africa or in Germany. So this is why the ISP-location awareness does not work out. Okay, the other awareness is the latency awareness. Yes, a peer may benefit from the latency awareness where a node connects to low latency nodes. Yes, it is very expensive to measure, like I said, the latency to every node. So we use here something like a landmark-based prediction method. Yes, I want to explain this example. So how does this work? We have some landmarks mentioned as B nodes. B node 1, 2, 3, 5, 4, 5. And these are, for example, public available servers which peers can ping to check the latency to this server. And yes, the positions of this B nodes, landmarks, are well known, and according to this, a node can determine a pseudo-location. Okay, and this pseudo-location can be compared between other nodes to find low latency nodes. For example, this host may have a low latency to this and that landmark node, a bit higher to this, and very high to this one, so he can say, okay, my pseudo-location is, for example, here, and I will connect to nodes which have a comparable or are nearby my pseudo location. Okay, now we have the evaluation of the underlay aware routing. Yeah, the good things are that we decrease the delay per hop, and it might turn a 6-hop path shorter in time than a 3-hop path. So for example, a 6-hop path with 20 milliseconds is better than a 3-hop path with 100 milliseconds. Okay, and it is often easy to apply if we have a selection. So we can select nodes, for example. Yes, we can pick, for example, in chord, a finger in a range, not only one node. And for example, the overload of zones, the improvement, here we can also pick nodes from the neighboring virtual nodes. We have also some shortcomings. Yes, the obtaining of underlay information is costly. Yes, either through measurements or through cooperation with ISPs, but the cooperation with ISPs is very difficult. And the measurement sometimes is quite difficult, but there exists, for example, this landmark routing, landmark-based latency matching. And not all overlays support selection choice. For example, in CAN, so the vanilla CAN, original CAN, it is very difficult to choose a neighbor on your own as they are predefined and given. Okay, the next improvement yes, are buckets instead of entries. So the motivation is that if we just use entries in our routing tables, for example, one single node might fail. And if we have several nodes, they are less probable to fail. So we can choose from a bucket. This is called a bucket. Okay, the idea is yes, to use a bucket instead of single entries in a routing table. And in case of a node failure, we have enough time to back up this bucket. Okay, yes, an example we have here with Pastry and Kademlia. Kademlia got buckets instead of one entry, so it improves its robustness. Also, we have an example in Chord. We can use a successor list instead of just one entry, because if this entry fails, we have a problem, because we have to contact, for example, a finger or so. And the successor list is pretty robust. For example, OpenChord uses a configurable successor list with the length of 2 as a default value. Yes, 2 is enough, I think, because the nodes in the chord are located randomly, so it's very improbable that 2 nodes with which are successors might fail at one time. Okay. So the benefits of buckets instead of entries, the routing continues in case of failures, and we can fix this. We can fix our bucket, and direct rebuilds are possible. We have also some shortcomings. For example, we have the increased maintenance overhead, because we have to maintain our bucket. And we have more node state, sure. And this demands for more storage, but it's not very drastic, so it's nowadays this might be outdated. Okay, another improvement are parallel lookups. The motivation is that several lookups in parallel are less likely to get stuck or delayed. The idea is to, first of all, we require buckets to use parallel lookups, and we send lookups, several lookups in a corresponding bucket. This is just like in Kademlia, routing Kademlia, we have parallel lookups there too. What is good? It is very fast, and it's the most reliable lookup succeeds first, and we have less effect of routes with slow or malicious node and message loss. So as we use parallel lookups, they might go different ways. So if we have a malicious node there, maybe a lookup can be dropped, but the other lookup may reach its target. And we have some shortcomings. This is the increased overhead, as yes, the lookups are parallel. So this is a trade-off. We have the bandwidth on the one side, and on the other side we have the reliability and application experience. And the reliability and the application experience is very important, as the user may stop to use a service if it is very slow or unreliable due to message loss, for example. Okay, this is yes, okay. So now we have the how can we route in our overlay? So we have different ways to route. We have 3 approaches. First of all, the recursive routing. This is this is used in chord, can, pass-tree, for example. And yes, we have here our chord ring, for example. We are this node, and we just forward the lookup to our fingers, and the target responds with the object. We have here a plain path length, and we have to trust intermediate nodes, as they might just drop the packet or the request, and we have to wait for a timeout and start the lookup again. Then we have the iterative routing. There we have more control about the routing process as we contact every node on this routing path. First of all, we contact this node because our finger table says this is the node we have to route to. This is our next hop. This node might say that my next hop would be the node 1622, and this information is this information is passed to the query initiator, and he decides whether he wants to route to this node. Then he, for example, can route to this node. Again, the the node says, okay, I want to route, so the next hop would be this node, and again I get the information and so on until I until I reach this target node. The shortcoming is that the path length is doubled, but we have more knowledge on the route because we contacted several nodes, and the intermediate nodes can be validated. So we contact every intermediate node to ask which is the next hop. This is increasing the robustness, as a node may, for example, this node 1622 may say, okay, the next hop is 659, and this node can validate this and can say, okay, this is not true, this is false, so this might be a malicious node, for example, and can look up for another node to continue this process. Okay, and then we have the tracer routing. This is something like a mix between the iterative routing and the recursive routing, because the node, the routing process is still recursive, as you can see, and every node is telling the query initiator what is the next hop. So, for example, if we get the information about the routing process, so we get the trace. So this is why the tracer routing. Again, we have plain path length. And the querying nodes can check whether signal path is used. So, for example, again, we can have a malicious node here, and the query initiator, for example, this node drops this message, and we know that the node 1622 wanted to forward this query to this node, but he didn't respond, or he didn't forwarded it. So we can choose another node. So we can continue in this this routing process, and not we don't have to. So yes, we have to wait for the timeout, but then we can continue where we just stopped. Okay, the P2P improvements are finished now. We saw the caching, so we cache objects to speed up the retrieve process. We saw the replication, so we replicate objects on additional nodes on different places. The dimension and realities, overloading zones like in Omicron with virtual nodes, buckets, and routing mechanisms. Yes, so we have now a series of overlays and improvements of them, which can be used to build a peer-to-peer network. Yes, the improvements depend on the actual use case. For example, if an object is no more available in the file sharing application, then this is not that crucial like in a social network where this might be the wall of a person. So it always depends on the application, which improvements or which overlay should be used. Okay, now the second part of this lecture is about the graph properties and distributions. First of all, we have some metric for graph evaluation. These are basics, and you should know them from your basic studies or bachelor study. I just go through and briefly describe those metrics. Okay, so we have the distance between two nodes, I and j. So this is the number of edges along the shortest path between these nodes. We have a diameter of network D, which is the maximum distance between any two nodes. Then we have an average path length L of a network. This is the mean distance over all networks. Yes, we have a total amount of nodes and all. Then we have this degree Ki of a node E. This is the total number of edges the node is attached to. The average degree of the network. This is again the average of all Ki of a network. And we have, this is probably new, the degree distribution Pk. This is the probability distribution of Ki. And this is new, I think. The clustering coefficient of a specific node is the number of links between all neighbors of a specific node between themselves over the number of possible links between all neighbors of a specific node. We have an example on this on the next slide. And the clustering factor of the whole network is again the average clustering factor of all nodes in a network. Okay, the clustering coefficient of one node. So how do we measure this? Okay, this is the This is the clustering coefficient, and it is calculated by the actual number of edges among k neighbors of a node. For example, here we have this is our node, and these are the neighbors of this node, and the actual number of edges among the k neighbors of the node are 1, 2, 3. Okay, these are the nodes between these 4 neighbors of our node. 1, 2, 3. Okay, and we divide this through the amount of the maximum number of edges among these neighbors. So the maximum number of edges between k nodes is k multiplied by k minus 1 divided by 2. We have here the example again, I think. Yes, we have this example again. Okay, I go through this fast. Yes, we have this 3 current edges. This is here, the upper part. And we have at most 6 edges with 4 nodes in a network. So we have a clustering coefficient of 3 divided by 6, so this is 0.5. Okay, do you have questions regarding this? Okay. So now we have an example for the clustering coefficient. We have a regular graph, which is yes, every node has 4 neighbors, which you can see here. Yes, every node has 3 neighbors, and the clustering coefficient of this node is yes, he has 4 neighbors, and these 4 neighbors are has 1, 2, 3 edges, and again we have 4 neighbors, so the maximum number of edges between these 4 neighbors is 6, and we have again a clustering coefficient of 0.5, and because this is a regular graph, the clustering coefficient for the whole for this whole graph is again 0.5. Yes, all nodes have the same clustering coefficient. All right. Okay, now we come to the what Strogatz process. So this regular graph can be modified and rewired. Here we have the rewiring probability. So to the right it gets higher, the probability. Here we have a graph which is slightly rewired. So we just took some edges and rewired it. And here we have a random graph if the rewiring probability is very high. So the what Strogatz process is that we randomly select an edge and randomly rewire it with different nodes. For example, here we had this edge and we rewired it that now we have an edge here, and this edge is from somewhere else, I don't know where, but it's okay. So what is the effect of this process? Again, we have here the clustering coefficient and the path length for this 3 different graphs. So through rewiring, we get from a high clustering coefficient to a low clustering coefficient, and from the high path length to a low path length, if the rewiring probability is high enough. So somewhere in the middle, so the slightly rewired graph, we have a high clustering coefficient and a low path length. So the path length gets low if we have some shortcuts here in this regular graph. And this is what we need. So a high clustering coefficient and a low path length is the sweet spot, because the clustering coefficient is somehow defines the robustness of the graph. So this is somehow how well your nodes are interconnected. So if you fail, the nodes are, if they are well connected, they can route around you. And a short path length is, yes, we can route faster through this graph or network. Okay, here we have some examples for what Strogatz graph. Oh, okay. On the left side, we have 20 nodes with a maximum degree of 6. So we have we have 6 neighbors at maximum, and we have a rewire probability of 10%. And this even with 10%, we have this graph doesn't look like a regular graph. And on the right side, we have a graph with 100 nodes and a maximum degree of 30, and again a rewire probability of 10%. And as you can see, it's pretty random. Okay, what is the result? So here we have the effect of the rewiring and the clustering coefficient and the path length. We can see on this graph the on the x-axis the probability of rewiring with logarithmic scaling, and on the y-axis we have the clustering coefficient. The blue is the clustering coefficient, and the red is the path length. As you can see, we first started with if we have the small probability of rewiring, we have a high path length and high clustering coefficient, as you can see here. And if we increase this probability of rewiring, the blue, so the clustering coefficient goes down, and the path length also goes down. So the sweet spot is maybe somewhere here, where we have still a high clustering coefficient and a low path length. Okay. So the sweet spot here is, for example, by around 1%. Yeah. Okay. Okay. The problem on these graphs of what's triggered is that practically we don't know how the graph looks like, so in the praxis. So now we want to check what graphs do we encounter in the praxis, but we will come back to this graph. So, okay, in the reality we have the so-called small world graphs. So which characteristic do those small graphs have? First of all, they are somehow clustered, like you see on this picture on the right here. And we want to understand why. So we have this cliquish graph. So you can imagine that those cliquish graphs represent somehow social cycles, where friends are tightly connected, and between those tightly connected circles, for example, this one and this one, that does only exist one edge. So between those tightly connected cycles, there are just a few connections. But still, we have a small diameter, since the distance is small between the most part of peers. So, for example, yes, so we can reach this from this edge and so on. Okay. Okay, those small world graphs can be modeled with power law graphs, which are scale-free. Here we have a picture how such a scale-free network looks like. So this is the picture. So what do we mean by power law? With power law, the probability of having k contacts should be equal to k to the power of minus gamma. This is what is mentioned here. So this gamma may vary, and possible good values are 2 or 3. So this means that there are only a few nodes with a high node degree, but the most nodes have a low degree. So you can see this here. We have very much of this this edges, this leaves, and so they have only one connection, for example, and we have only one node with a very high node degree. Okay, the characteristics of the power law distributions are we have uneven link and load distribution, as you can see here on the graph, but it supports heterogeneity. And another shortcoming is that it is very fragile to attacks, because if we turn off this high degree node, the whole network may collapse. Okay, here we have some examples and characteristics of small world and scale-free networks. Yeah, an example is that the most World Wide Web pages are reached via 70 to 19 hops. Yeah, the phoning in the US is small graph 2, for example. Yes, there are a lot of examples. For example, yeah, this is also very interesting, that the movie relationship between performers are 3 hops. So, for example, the Star Trek actors mostly made movies with each other, and yeah, so we have also some actors that connect all other actors. So these actors are yeah, never mind. Okay. Okay, and the characteristics is that yeah, they are clustering, where they have a strong local interaction and they are clickish, and the connectivity and the degree of the nodes. So we have a few high degree nodes and many low degree nodes. So why do we use scale-free networks for peer-to-peer networks? Yeah, because of the fault tolerance, which we get with the high clustering coefficient. Through this, it is robust against random faults, as I said before, at attacks, and uncertainty with faults at highly connected nodes. Also, we can optimize some search mechanisms in scale-free networks, for example, with the random walk or the high degree search, and so on. Also, why Wet-Strogat's graph are not good suitable, because those static networks cannot model dynamic real-world scenarios. So the Wet-Strogat process is designed for an existing graph to start the rewiring. So also, Wet-Strogat's graphs do not represent human behavior. So we are not like have all an equal number of friends and just randomly create contact to other persons. So we have an extension from Barabashi to turn those graphs into graphs with a power law distribution. So we have these 2 techniques from to turn this graph to Barabashi graph. To support the dynamic growth, we construct the small world graphs dynamically, so nodes can join this graph, and we do not rewire the graph as the Watts and Strogat's process do. Also, we have a preferential attachment, so we attach ourselves to nodes which are very good connected, so which have a big neighborhood, and we do not do this randomly. Okay, this is how Barabashi graphs look like. It's with n equals to 20 nodes and a maximum degree of 7. These graphs look like this. So we have 1 one node which is very good connected, and for example one node which has just one edge. And yes, here we have a Barabasi graph with 100 nodes at a maximum degree of 30. Sorry. Somewhere in the middle there's and yeah, there are a lot of points, a lot of nodes which has a big neighborhood, for example this node. But there are also nodes which are again which has only one connection. Okay. Okay, this slide is kind of a duplicate. Yes, about the distribution of the node degree. So this pk is the probability that a randomly selected node has exactly k edges. Okay, we have here a distribution of the node degree in social networks. This is an example. And here we have measured how many persons call other persons in a log-log scale. Here we can see that plenty persons called just a few persons, and only a few persons called lots of persons. So for example, here we have a person that calls a lot of persons. Okay. So we have again somehow a ZIP distribution. Sorry. Okay, here we have something similar, only with node degrees and not calls between persons. And again with a log-log scale. So we have on the x-axis the links and on the y-axis the nodes. This time the small part of nodes have not that much links, but this is somehow similar to the figure before. So we don't have Okay, this is the last slide for today. Okay, why do power law networks exist? This is because new persons want to connect to existing social circles in real world. And in peer-to-peer networks, the networks grow continuously, and new nodes are preferable attached to well interconnected nodes. A good example is Nutella, where we attaches to nodes which are well connected to so we get a lot of response. And these nodes are preferred with regard to setting up new connections. So this node has a big neighborhood, so we can set up a lot of connections. Okay. All right, we are ready for today. Thank you.